hi guys, welcome to workshop. So I'm basically just going to go through the questions that I sent along with this email. So hopefully you've had a look at them, maybe you've had a try of them, and hopefully I can answer any kind of like questions that you've got. So Richard is also, I think he's kind of put a little message out. Richard's on the chat facility. So as I'm talking through this, if there's anything that you're kind of unsure about or you're struggling with, just type him a message and hopefully he'll be able to answer it, or at least he can come to me and basically say, Kim, explain this a bit better. We think. Righty-ho then. Okay, let's get on with this. So I think there's only like 4 questions, isn't there? So hopefully a little bit of mixture of everything. So the first question in this pack was on isomerism. So it wasn't just a bog standard case of deciding whether this was E or Z, which is usually kind of like a common like 1-mark question. We actually have to explain whether this compound is E or Z and then write its IUPAC name. So right then, so we need to kind of basically talk through the steps regularly working out E and Z isomers. So first thing in the question, it's on about this Carn-Ingold prelog, the priority rules. So if you've forgotten what those priority rules are, this just means that the highest atomic number is your priority group. Okay. And what I mean by priority groups, I just mean this will help us decide whether a particular alkene is an E or a Z isomer. If the priority groups are on the same side, or same side, then it'll be a Z isomer. If they are on opposite sides, it will be the E isomer. So we basically have to explain what we are doing. So I'm just gonna label my carbons now. I'll just kind of like talk through it. So first thing we need to do is we have to talk about each of the carbons in the double bond separately. So first off, I'm probably going to talk about the carbon on the left-hand side. So I'll give that a little highlight. There we go. Checking that's the right-hand side. So first thing I'm going to do, my first bullet point, I'll be considering. So consider the carbon on the left-hand side. So the left-hand side of the double bond. So we need to look at. Oh, hello. Need to do that one first. So what is that carbon attached to? So it's attached to a carbon at the top and a carbon at the bottom. So this carbon is attached to 2 carbons. The carbons have the same atomic number, so we can't decide which one's the priority group here. Right, so if that's the case, if the carbon atom is attached to the same group, we have to then go down the chain. So we're going to go along that chain. So if we go along that chain, this one is attached to 3 hydrogens. This one is attached to a carbon and 2 hydrogens. So down the chain, with the top one, we are attached to a carbon. At the bottom, we're attached to a hydrogen. So we need to put that down, don't we? So first of all, we have to mention the first carbon. The carbon is attached to 2 carbon atoms with the same atomic number. So that's what we did at first that I just forgot to write down on the drafty. Right, so because they've got those carbons have got the same atomic number, we now have to look to the next atom in the chain. Okay, so we can look to to the next atom in the chain. In the top group, it is carbon. In the bottom group, it's a hydrogen. So now, because we've gone to the next atom in the chain, that next atom is different. In the top group, it's a carbon. In the bottom group, it's a hydrogen. So the carbon has the higher atomic number. So the CH3, CH2 group is the priority group. Moving on there. So I've identified that top group, the CH3, CH2 group, is the priority group. So do you know what I'm going to also do? Give that a number 1 at the top. Just so I remember it when it comes to the very end, because I'm going to have to name this whole thing. So the carbon has the highest atomic number, so the CH3, CH2 group is the priority group. Yeah. Cheers, Richard. Right, so we've considered the carbon on the left-hand side, so we now have to look at the carbon on the right-hand side. So this one's a little bit easier. Because that particular carbon that I've just highlighted in green is attached to 2 different atoms already. So at the top we've got a carbon, at the bottom we've just got a hydrogen. So we can see that straight away that the top group will be our priority group because carbon has a higher atomic number than that hydrogen. So if I want to write that out, I do want to write that out, we need to consider the carbon on the right hand side and the carbon is attached to a carbon atom and a hydrogen atom. The carbon atom has a higher atomic number, so just double check what group it is, CH2OH. CH2OH group is the priority group. Cool. I feel like I filled this in already. So, going back to the top then, we have kind of like worked out and explained that those 2 groups at the top are the priority group. So that's with the 1s on. The 1s just represent that they're priority groups. So the priority group is the same. So it is a Z isomer. So we just have to kind of summarize that at the bottom. So I'll put at the bottom, both priority groups are on the same side. So the isomer is a Z isomer. Okay. Right, so this is one thing that I forgot to do when I was looking through these questions. So, because you do all that writing, you kind of forget what the whole question is. So it's always good to just kind of going back and check. So we've explained how our priority rules can be used to deduce the full IUPAC name, but we have to give the IUPAC name of this compound. I do believe that is one of the marks to actually give it. So one of the marks is to actually give the IUPAC name. So this looks like a bit of a scary thing when it's like this. So we have to identify, we already know that it's an alkene because it's got that double bond, but we have to just have a nosy to see if there's any other functional groups. So there is. There's a little OH group, so it is an alcohol. So we've already established that it's an alcohol, so the end of our name will obviously end in ol. We then have to work out how many carbons there are in the longest chain. So we've got 1, 2, 3. If we go down to that one, there's only 4. If we keep going on here, there's 4 and 5. Okay, so our longest chain contains 5 carbons. So we need to use that prefix pent. Right, so obviously if this was just a regular alcohol, it would be pentanol. But because we've got that double bond in there, we need to say it is pentanol, okay? So that is important, that EN rather than AN, okay? So because we've got that double bond in, it's pentanol rather than pentanol. And there's also something that I've forgotten to put in that pent, where the double bond is. So I've forgotten to put where that double bond is, typically. So the double bond is on the 1, 2, the second carbon. Okay, so about the pent. So on there, going off it again. So pent because there's 5. A number 2 in there because the double bond is on the second carbon, EN for the double bond, and then ol because there's an alcohol group. So there's a lot of different things going into this naming thing. So we've got alcohol, ol, penten because it's an alkene, not an alkane. And oh, sorry.
And where the ol is.
Do we have to put where the ol is? Oh, we do need to put where the ol is. Oh, goodness. On there as well. Thanks. Had it written down. So we have to put the 2 where the double bond is, and then the 1 where the ol is. So it is super duper kind of tricky on there. So pent 2N because the double bond is on the second carbon, 1 ol because the OH group is on the first carbon. So we do have to count from that OH group because that's the main functional group in this. It takes priority over the alkene. If you're unsure what takes priority over each other, in your introduction to organic chemistry, when we did the list of the names, that tells you kind of what is usually numbered first. So alcohols are usually the numbering system starts from the alcohol rather than the alkene in there. So pent 2N 1 ol. Still more to it, guys. So we've got pent because we've got 5 carbons, 1 ol alcohol on the first carbon, double bond on the second carbon. Right, one of the carbons we didn't kind of make into the mix down here. We've got a methyl group as well. So we've got a methyl group as well, and we need to say where that methyl group is. So 1, 2, 3. It's on the third carbon. So 3 methyl pent 2N1 ol. One more thing to add to this lovely name, right? It's a Z isomer. I think because you've stated it's a Z1 at the top, you probably wouldn't have to put it in, but I'll just do it just in case. The mark scheme didn't put the Z in, but I'm putting it in there. So Z, 3 methyl pent 2N1 ol. Massive mouthful. So there's 6 marks. So you had to basically, to split it up, you had to talk about the 2 carbons separately, the one on the left hand side, the one on the right hand side, identify which one of the priority groups were. So the priority groups for The one on the left-hand side was the ethyl group, the CH3CH2. Both carbons were attached to that carbon on the left-hand side, but when we moved down the chain, we had two H's and a C rather than 3 H's, so that top one took priority. Then when we went onto the carbon on the right-hand side, that was a little bit easier. That carbon was only attached to either a carbon or a hydrogen. Carbon takes priority because it's got the higher atomic number. Whew. Written it all down there. And I went over the lines. That's the way it goes. Cool, so that was the big kind of 6 marker on there. Thanks, Richard, for the little dancing man. Okay, so nice big chain, and it's given it this terrible biology name that I'm scared of. Oleic acid. So C18H34O2. So it is a straight chain fatty acid. Okay, don't be scared by the term fatty acid. It's just super duper long carboxylic acids. Okay, and it's obtained from plant oils. So isooctane can be made from oleic acid, and this is the skeletal form of it. Right. So there's a lot of information in there that possibly we do not need. Do we actually need to know all that stuff? So it's a case of sometimes there's lots of words that you might not have come across, and it's a case of not to be freaked out by it. You just need to be confident that you can look at that structure and you can see a double bond, so you know there's an alkene, and then down here we've got a nice carboxylic acid group as well. So you've just got to be clear that, well, this has either got something to do with alkenes or something to do with carboxylic acids. Don't be scared because it's a really kind of like large structure. So let's actually look at the question. Right, identify a reagent that could be used in a chemical test to show that oleic acid is unsaturated. Right, this word we do have to be confident with. Right, basically unsaturated means we've got a double bond in there. Right, there are 2 functional groups in this compound. There's a carboxylic acid and an alkene. So if you're not comfortable with that term unsaturated, you don't know what you're testing for. So we want to test for an unsaturated compound. So we want to look for a double bond. So got to think of all the tests that we've kind of looked over. I think this is a nice one because it's I think we use it at GCSE as well. So reagent, that bromine water. Yeah. Okay, so bromine water could be used to test for a double bond. Just on there, I don't know what's wrong with that. Right, so you can either write it as bromine water, or you can write Br2, or Br2 aqueous. Okay, don't put Br. Don't just put Br on its own, you will get an incorrect mark. You might get a right mark for the observation, but if you just put bromine down as Br, that will make you lose a mark. So, observation, what happens? Right, it starts off orange, bromine water is orange, and it goes colourless. Not clear, colourless, okay? Clear would not get you the mark. Okay, changes colour. You could also put decolorizers. That's another way of doing it. Or loses its colour or something on the lines, but orange to colourless pretty much tells us exactly what it's about. Cool. So that's quite a nice easy 2 marks. It's quite pleasant, okay? It's just that you've just got to be clear what unsaturated actually means. Right, so question 3, so a completely separate question. Right, we've got an alkene, 3-methylpent-2-ene. Right, that looks like that. And it reacts with hydrogen bromide to form a mixture of 3-bromo, 3-methylpentane, and 2-bromo, 3-methylpentane. Cool. So, first off, the question tells us that the alkene, so the alkene that at the start of the question, exists as E and Z stereoisomers. Right, it wants us to draw Z3-methylpent-2-ene. Okay. Right, if it is a Z structure, okay, this is, when you want to draw a definite Z structure or a definite E structure, it wants you to show the stereoisomerism. It's really important that when you actually draw it out, what I like to call the little star shape. So the double bond in the middle and the groups going off the sides like that. Sometimes if you kind of draw it as a straight chain molecule with just displayed formula, you don't get the marks because you don't necessarily draw it as an E or a Z isomer. So it's really important that it's drawn out like that. Problem is, not many people can sometimes see that whole molecule in that form. So I always have a go at kind of drawing it out to begin with. So either at the side or somewhere where it can fit. So I would probably draw this thing out in full so I can kind of transfer it from that structural formula into that little kind of like star shape. So I can draw it as a Z isomer. So I'll just draw it out displayed. So this thing, we've got a CH3, we've got a carbon that's bonded to one hydrogen, and it's got a double bond to another carbon. Right, that carbon there is bonded to a CH3 group and a CH2 group. So if I just highlight that, so we've got CH3 group in green. Okay, so both those groups, the thing I've highlighted in the green, the thing I've highlighted in the yellow, are attached to that carbon with the blue dots over it. So when I draw it out, I'll have a CH3 attached to that carbon and a CH2 over there. So I always kind of draw those structural formulas out into kind of like a displayed kind of formula way so I can actually see what's attached around my double bond. So I've actually done that. So I've got my carbon-carbon double bond here. So I can draw that out in the middle. C double bond C. On this carbon on this side, it's attached to a hydrogen and a CH3 group. And on this second carbon over here, that's got a CH3 group and a CH2 group. So that's how we would draw it out in kind of that format. So this is kind of just all my little bit of working, because sometimes it's a bit difficult to draw those actual structures straight from kind of this version into that version. So that's just the way I kind of set it out. Right, so I can get rid of that now. I've obviously done this in pencil, for example. Right, so now I've got my structure like this. It wants me to draw the Z isomer. So I need my priority groups on the same side. So let's have a look at this one here. So this carbon's got a carbon and a hydrogen attached to it, right? That's my priority group, CH3 over there. And then let's have a look at this carbon on this side, right? It's attached to the two carbons there. Okay, so I need to have a look at it. So then we've got 3 hydrogens as opposed to 2 hydrogens and a carbon. So because we've got 2 hydrogens and a carbon down here, this one is my priority group. So the way I've drawn it, I've got my priority groups on the same side. So I actually have drawn the Z isomer, even without thinking about it. So it can be drawn like that, or just as long as the priority groups are on the same side. It doesn't matter. Either one of those will get you the mark. All I've done is just put the priority groups on the top rather than the bottom this time. So yeah, so either one of those will get you the mark. So with these questions, I wouldn't shy away from them. I wouldn't worry about them. If you're not confident with putting those structural formulas directly into kind of that format, just draw it out. Draw it out of the side. Just draw it, scribble it above into the question, okay? I just had to draw it down in the answer so I could actually, so it's nice and clear for you guys. You could just kind of draw it out up at the top up here somewhere. Right, cool. So, one mark for that. So priority groups on the same side. I don't think I need to say anything more about that one, do I? Oh. Skeletal? Oh. Why are we, oh, Richard's making me do skeletal. Right. Hope everyone's okay with that. Shall I just draw it out? Skeletal. Oh, how mean. How mean of you. Oh, goodness. Right. So Richard's making me do skeletal now. Ah! Go away. There we go. Right, skeletal. So, right, we've got carbon-carbon double bond, like that. Right, in the case what I've drawn down there, I've got a CH3 going down and a CH3 going up, and then going down in the opposite direction. Oh, no, I didn't mean to do it like that. Ignore me. My pretty little drawing. Okay, so I've got one going down, one going up, and then down here I've got a ethyl group. So obviously we've got nothing over here because when you draw skeletal you don't draw the hydrogens, so it's left up there. I've got a methyl going down, which matches what's over here, and I've got an ethyl over here, which matches over there, and the methyl going up. And again, you can draw it the other way around as well. So with the ethyl and the methyl on the top, and then the methyl at the bottom. See, that would be 3 steps for me, because I don't think I'd be able to convert the structural formula directly into skeletal. It's just sometimes a little bit hard to see. So skeletal or that structural flash display should get you a mark. Soz. No, the workshop, I need to do it. Right, okay. So skeletal and then the displayed one. Right, so it did mention something about in the question. It says there's a bromo in the thing that it makes. So going back to the start of the question, alkene kind of reacts with hydrogen bromide to form a mixture of 3-bromo 3-methyl pentane and 2-bromo 3-methyl pentane. So because I see that we're going from an alkene to a halogenoalkane, I'm thinking, oh God, there's going to be a mechanism in here. Yeah, there is. So, name and outline the mechanism for the formation of 3-bromo 3-methyl pentane. Right, again, if you haven't got a Scooby-Doo what 3-bromo 3-methyl pentane looks like, just draw it out. Draw it out in your kind of answer. So pentane, we've got 5 carbons. I think I've done that too high. Wonder if I can, do you know what? I'm just going to draw it on a separate piece of paper. I know you guys don't get a separate piece of paper. But me. 2, 3, 4, 5. Right. 5 carbons. 3-bromo 3-methyl pentane. So basically, on the 3rd carbon, I've got a bromo group and a methyl group. So this is what I'm going to make. Don't forget your hydrogens. Right. So some of you probably can read 3-bromo 3-methyl pentane and know exactly what it is straight away. If you have to draw it out, you have to draw it out just to know what you're kind of going to get. So that's what I'm going to try and make. So that means that the double bond that was broken, I'm going to add a hydrogen over on the 2nd carbon, and that means that the bromine is going to have to jump onto the 3rd carbon. Right, that is important when you're drawing out your mechanism, because you need to make sure that when you draw out the mechanism, the intermediate is going to match what you're going to end up with, okay? So when you do your intermediate, you have to make sure that your bromine can go onto the 3rd carbon, okay? So let's go through that kind of mechanism. Right, so name and outline the mechanism for the formation of 3-bromo methyl pentane. Right, so alkene to halogenoalkane, looking at electrophilic addition. I was about to say substitution because we've been doing benzene, haven't we? But that's wrong. And hopefully someone could tell me, but we're not doing aromatics, so I won't dwell on it too much. Okay, so electrophilic addition. Right, we are using an electrophile, something that likes electrons because we've got that double bond there. So lots of electrons in that double bond, so it's going to react with things that likes electrons. And we are adding to our compound, okay? When we're going from an alkene to a halogenoalkane, we're just adding things. So that's why it is electrophilic addition. Right, so what we're starting with, that thing that we made before, wasn't it? Yeah, so let's start with our compound. We drew it earlier, didn't we? CH3 and a hydrogen there. And then it was, what was it, CH2, CH3. So we drew it on the last example, so you should have that kind of all drawn out and ready to go. Again, I like to kind of draw it in this format. It's just easier kind of like to draw out when you do the alkenes and stuff. Right, so we're told it's going to react with hydrogen bromide. Right, it does say it up here, okay? So, reacting with hydrogen bromide. So, hydrogen bromide, we've got a hydrogen in and a bromine group. Right then, I feel like I'm going to lose space here when showing this mechanism. Right, so in hydrogen bromide, we've got a difference in electronegativity, so we actually have some partial charges on our atoms. So we've got a slightly positive hydrogen, a slightly negative bromine. So in that double bond, like I said before, we've got a nice amount of electrons just kind of moving all around. So those electrons are going to be attracted to that slightly positive hydrogen. So I'm going to draw our curly arrow from our double bond to our hydrogen. Right, what's that showing? It's showing the movement of those electrons in that bond, okay? Breaking off and forming with that hydrogen. So basically that is showing us forming a bond between one of those carbons and that hydrogen, okay? So hydrogen has kind of got a new mate now, so it's going to join with that big molecule. Doesn't need bromine anymore. Hydrogen only forms one bond, doesn't need bromine. So bromine is going to be booted out. So we're going to draw an arrow from that hydrogen-bromine bond towards bromine. So hydrogen's found a new set of friends, bromine's going to leave and take its bat and ball with it. In other words, it's electrons. So that arrow is showing the electrons going from that hydrogen-bromine bond to the bromine. So hydrogen's found some new friends, bromine's going to take its bat and ball home with it. Right, so let's draw this structure out. So we've got our carbon. It's bonded to a CH3 still, that first carbon there. It's bonded to our hydrogen, and then we're going to pop that hydrogen that we've just added, okay, with that curly arrow. I've said we've formed a little bond with that hydrogen. I'm just going to add it to that first carbon. Right, we've broken the double bond, so we've got just a single bond between those two carbons. Draw it out. That's also bonded to a CH2, CH3, and also another CH3. So we've now got an intermediate structure. Oh, and don't forget that bromine guy with his bat and ball, or his electrons. Right, so now we've got a carbon that's got 4 bonds, so that's okay. We've got over here a carbon who's only got 3 bonds, and it lost its electrons, didn't it? Those electrons went to that hydrogen and formed a new bond. So that carbon's got a little plus on it because it's electron deficient. Right, so remember what I said, we had to make sure that the bromine was going to go in the right place. So we were told in the question which compound we were going to make, 3-bromo, 3-methyl pentane. So we had to make sure that that bromine is going to attach itself to the 3rd carbon along, which it is going to. 1, 2, 3, on 1, 2, 3. Okay, so you had to make sure that that little plus was on the correct carbon, on the 3rd one along. So with this kind of question, you have to be confident in what you're making and the actual mechanism itself, so you know where each of these different parts is going to be kind of placed. So my bromine's a little bit negative, it's got a nice long pair. Carbon is electron deficient, so now bromine's going to share its electrons with that carbon and hopefully form what I said we were going to form before, didn't I? CH2, C, CH3, Br, CH2, CH3. Sorry, it's a little bit messy. I got a bit too excited with the first part. Actually, I'll move that along. It's a bit messy like that. Oh, no, I'm taking that with me. Okay. So, does that match what I made earlier? What I said I was supposed to be making? It does. This is good. So, you have to be really careful when you do these kind of mechanisms. If it's telling you which one to make sure that the carbocation intermediate that you have formed will make that particular end product. So that's why I kind of drew that out in the first place. Just checking if I was okay. Does Richard want me to do it skeletally now? Just don't do mechanisms skeletally. Right, cool. So we've done the mechanism. So we've had to kind of think of a few extra things to kind of go along with that mechanism. We had to make sure we were making the correct product today. Right, there's some writing down here, so I'm guessing we have to explain something. Oh, we do. So we have to explain why more 3-bromo 3-methylpentane is formed in this reaction than 2-bromo 3-methylpentane. So we were told in the load of writing at the beginning that actually we do make 2 different products. We do. The hydrogen has a choice of which carbon it's going to attach to. It could go to here, it could go to here. Okay? In our particular case, we put it on this kind of first one down there because that's the carbon the hydrogen had to attach to form the correct carbocation to form the product that the question was asking for. So that's kind of what we have to do. But the hydrogen could have gone in either one of those. Right, we have to explain now why that 3-bromo 3-methylpentane is formed in the reaction. So basically, we have to explain why more of this thing that we've made is made in our reaction. Right, so it's all down to this, carbocation. Okay, it's all down to that particular carbocation that we formed in the second step, and how stable that carbocation is. So obviously it's not a stable molecule, it's got that plus on it, it's like freaking out. So there are things within that compound, oh God, why do I keep pushing on? There are things within that compound that kind of make this version that we've drawn a bit more stable. And it's all to do with how many carbons are attached. So in this particular case, our 3-bromo 3-methylpentane is formed via this carbocation up here. And this carbocation, the carbon with the plus on, is attached to 1, 2, 3 other carbons. So this particular product is formed via a tertiary carbocation. Okay, so 3-methyl. Nope. Oh, there's me laughing at Rich for doing the wrong thing last week. So 3-bromo 3-methylpentane is formed via a tertiary carbocation. Right, common things that people make mistakes in this type of question. They say that 3-bromo 3-methylpentane is the more stable carbocation. It's not. 3-bromo 3-methylpentane is your product. It is not a cation. It is formed via a tertiary carbocation, but it's not itself the actual carbocation. So that's the common mistake people make. So this formed via is kind of like an important thing. So 3-bromo 3-methylpentane is formed via a tertiary carbocation, which is more stable than the secondary carbocation that forms 2-bromo 3-methyl pentane. Or you could say that 3-bromo-3-methyl pentane is formed via a tertiary carbocation. The 2-bromo-3-methyl pentane is formed via the secondary carbocation, and the tertiary is more stable than the secondary. So there's a few different ways you write it. You could even just say that 2-bromo-3-methyl pentane is formed via the secondary carbocation, which is less stable than the tertiary carbocation. Right, do you know what? Even though it's not kind of part of the question, all it just wanted to do was state, I'll just kind of go over why, might as well. This is a tertiary carbocation that we've got up here. So like I said, there's 3 carbons around this carbon with a plus. If we did it the other route, I'll just get rid of this for this time being. Just prove to you. If the hydrogen went on the second carbon, like that, this would be the other way that we could, this would be the other product kind of route. Bromine would attach to that carbon. This particular carbocation, this carbon here with the plus on, is only attached to 2 groups. So that makes it secondary. Right, so I'll just get rid of that. So just proving to you that one is the tertiary, one is the secondary, just in case you didn't believe me. Go back. There we go. Right, so why is this version more stable? Basically because it's got more carbons in there. It's got more carbons around that positive little carbon in the middle. Whee! So this is an unstable intermediate because we've got that little positive charge on there. And that little carbon's unstable. And the carbons around it can donate their electron density. So they kind of like push electrons towards that carbon. Obviously, electrons are negative, so they're basically trying to neutralize that little positive charge on that carbon. So they're trying to help out that carbon, make it more stable, giving them the electrons. Because I'm tiny bit superficial, I used to kind of like think about it as I'm the carbon with the plus on, and I'm wanting to go out and I can't find a new outfit, okay? So all the other carbons are kind of like my mates trying to offer outfits to go out in on a night out. So obviously the more friends I have offering me outfits, the more kind of stable I do become. Again, I told you it was a little bit of a superficial kind of analogy. So obviously the more carbons around there, the more the electrons are kind of being pushed towards that positive carbon, so the more stable the carbocation is. Not saying that it's just like a stable compound, it'll still react, it's just the more stable it is. The less carbons there is, the less chance there is of electrons being pushed towards it. And we all know that as the positive inductive effect. Cool. Oh, someone asking me a question. Oh, God. Friends? Oh, makes me sad. Yeah, I'm the most, I kind of form by the more unstable carbocation. I don't have that many alkyl groups offering me, I don't know, tops and hats. Yeah, anyway. Right, so I think that answers everything, doesn't it? Yeah. So name and outline. So I did name it, okay? Name and outline the mechanism. Whenever you see outline the mechanism, it wants you to draw the curly arrows. That is what I've done. I've formed the correct product via the correct intermediate, and then I've explained why that product kind of forms more than the others. Cool. Right then. So that's kind of like a trickier one. Oh, there's my little thing again. How exciting. Right, so last question, a bit about polymers on there. So I feel like sometimes this is part of the alkenes part that everyone kind of wants to forget. So this is so chloroethene can be polymerized to form polychloroethene, commonly known as PVC. So this picture on here is kind of what PVC actually looks like. So this polymer can be used to make pipes, window frames, and electrical insulation. Right, plasticizers can be added to change the properties of PVC. Okay, oh, plasticizers. Right, so it tells us that chloroethene, so that's the monomer, okay, so that's the thing that makes it. That's the kind of smaller molecule, has a melting point of 154 degrees C, and all types of PVC melt at temperatures over 100 degrees C. So that's just kind of a long-winded way of telling you that PVC melts at a higher temperature than chloroethene. So you have to explain why PVC melts at a higher temperature than chloroethene. So this is kind of going back to his bonding stuff as well. So bonding just kind of appears all the time in things. So it's 2 marks and there's a lot of lines for it. I don't think we have to write too much for it. You have to realise that PVC is a bigger molecule than chloroethene. So you have to be kind of aware, well, chloroethene is the monomer, so the one thing that kind of goes on and makes these endless repeating units of a polymer. So the thing about this is you have to be confident what a polymer is. It's made of lots of these alkenes in a really, really long chain. So PVC is a bigger molecule than chloroethene, right? So bigger molecule, greater MR, so greater molecular mass. So what does that mean? It means that your van der Waals forces will be stronger in PVC than they would be in chloroethene. So because PVC is the bigger molecule with the greater MR, PVC has stronger. Could say dipole as well. Van der Waals forces between the molecules. So obviously it takes more energy to break up PVC than it does the chloroethene. Okay, so stronger van der Waals forces between the molecules, or you could have just generalised and says PVC has stronger intermolecular forces. Entirely up to you which one we use. Entirely up to you what you use. So PVC, bigger molecule than chloroethene, so it's got a greater MR. PVC has stronger van der Waals forces or just stronger intermolecular forces between the molecules. It's just 2 marks. It just wants you to identify that the polymer is bigger, and that means it's got stronger intermolecular forces. Right then, so that wasn't too horrible. The polymer questions aren't too bad. Okay, so this is the structure of a molecule used as a plasticizer in PVC. Right, deduce the number of hydrogen atoms in this molecule. Oh, fun. So I think this is a tedious 1 marker, but you know what? It's a nice one because all you've got to do is count hydrogens. Right, so if you remember back, skeletal just basically shows us like the carbons. It doesn't show any kind of hydrogens in there. So me personally, I'd kind of just draw them all in and count them as I go along, pretty much. So carbon likes to form 4 bonds. So this end one has only got 1 bond to another carbon, so that must mean it has 3 hydrogens to it. So I've got 3 there. The second one has already got 2 bonds, so the other 2 must be to 2 other hydrogens. So there's that one and that one. Right, when we get to this particular carbon here, we've got a bond going down, 1 going up. So we've got 3 bonds there, so there's only 1 hydrogen on that bit. And it's on over. No hydrogens on that one, it would have kind of put it out there, right? This carbon, it's got 2 bonds to an oxygen, 1 up there, 1 down there. Nope. Not 1 on there. Right, we all know about this benzene now. So benzene, it's got those 3 double bonds. So all the carbons that haven't got anything on already have got a hydrogen. That's already got 4 bonds. That's already got 4 bonds. That one's already got 4 bonds. That needs 2 hydrogens, right? You've got 3, so you can have 1 there. You've got 2 bonds. There we go. Right. End carbon, got 3 hydrogens. You need 2, you need 2, you need 2, and you need 3. Right, so now I'm just going to do is just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, I got some missing on over. Should have 38. Did have 38 before. Oh, I forgot this guy. Forgot this bit. Look, there's a stick here that I'm totally missing. Right, one there, one there. So 33, 34, 35, 36, 37, 38. Boom. Don't forget a stick, guys. I knew I had one missing. I knew I just had to look at my little thing. There we go. So it's 38. Oh, did it right when I wasn't on camera. Whoops. So I just draw the little sticks on. I don't bother putting the hydrogens in, so it's just a thing, but I just draw the sticks of where they would be. And then I kind of put the dot next to them, so I just tick them off as I count them. It's one that you probably like to check towards the end. Right, okay. So, right then, so use your understanding of properties of PVC to explain whether you would expect to find a plasticizer in the PVC used to insulate electrical cables. Right, this is a good one for people who like have no common sense and no thinking. This is one where you kind of freak out and goes, I don't remember anything like this. Right, so to kind of deal with this, we actually have to know why we would use PVC to insulate electrical cables. So obviously it can't conduct electricity. Polymers don't do that anyway. So electrical cables, right. With most of your electrical cables, they have to be flexible. If you notice any electrical cables anywhere, they're all nice and flexible. So you have to be kind of just a bit aware of what electrical cables are and what they kind of have to be able to do. So they have to be flexible. Right, you also have to understand what plasticizers can do. So adding a plasticizer to a particular polymer basically makes them more flexible. So you just have to kind of have a little bit of understanding of what properties of electrical cables and also what plasticizers can do and link the two together. So use your understanding of properties whether you would expect to find a plasticizer in PVC. So would I? Yes. Why would I? Because plasticizers make PVC more flexible. So with all this plasticizer stuff, all you've got to be aware of is how plasticizers change the properties of polymers. What do they do? So you have to kind of remember what plasticizers do and how it would be useful. Obviously that wouldn't be so useful for other things like PVC. I'm trying to think. Window frames, you don't want them to be flexible, do you? You need them to be solid, so that wouldn't have plasticizers in. Right then, last of the 1 markers. So a section of the polymer, polychloropropene, yeah. A synthetic rubber is shown. So now you have to draw the displayed formula. Right, it's displayed. We have to show all the atoms and all the bonds in there. So it's not skeletal, so I don't have to draw that again. So we have to draw the displayed formula of the repeating units of this polymer. Right then, so we've got to kind of figure out where this polymer stops repeating, to be honest. Right, so here we've got carbon, that's the kind of like trailing bonds. So we've got carbon here, here. Right, where do we find that chlorine again? So that chlorine's there again. So we want to kind of break our polymer round about there. So basically I've just had a look at this polymer and just kind of broken it. Actually, maybe break it a bit. Broken it kind of where the repeating pattern kind of starts again. So now I've just got to draw this kind of little structure in terms of, actually break it. I don't know why I've broken it up like that. Break it up like that, should be fine. So I've got to draw this structure out as display formula. So I've got a carbon over there, bonded to a little carbon there, double bond, that side, and then we've got another carbon down here. Right, on my first carbon in that, I've got a Cl. That must mean I've got a hydrogen in that one. And then I don't forget, because it's a repeating unit, my trailing bonds. So you might have kind of picked out the repeating unit in the middle, because there's a couple of ways in which you could draw this. You could actually have that carbon chlorine as the ends on this side, and then your bonds kind of moving off. And then on this side, you just have to put that CH group over here. So that could have been another possibility. And they also have it where we can also have it where this one's the chlorine and this one's the hydrogen. I can't see that last one as well. I feel like the first two would probably the ones that I would go for rather than that last one. I don't know why it just would end up being like that. Oh, yeah. So 3 different ways you could kind of do it. So you've just got to make sure that because it's a repeating unit, you've got those trailing bonds off the end of the carbons. You don't need brackets, you don't need the N, because it's a repeating unit. Just checking that's not a question. So you don't need the, yeah, so you just need those trailing bonds. Brackets are not needed and the little N's not needed as well. Just as long as you've shown all the bonds drawn. Cool. So I think that's it now. So yeah, thanks for joining me, everyone. You must be still here, so that's good news. You didn't lose it when I started messing up the names, that's good. Right, so thank you for joining me. I hope it was helpful. I'll probably stick around for the chat for a little bit longer. If anyone wants to kind of stay on and ask any more questions, that is absolutely fine. But other than that, I hope it was useful, hope it was helpful. This has been recorded, so you can go back and watch it again if you want to. So thanks for watching, guys.